Hey everyone. So in this next video, we're going to talk a little bit about vertical projectiles. So this is kind of the last sort of linear motion type question that we can deal with. Um, we'll start off with this simple case of free falls and we'll build up from there. So we'll start with a standard free fall where the object's dropped, then we'll throw it down, and then we'll throw it up at the end. For the most part, they all get treated the same way. Now, typically, the free fall that we're really referring to kind of refers to any object that is falling freely, as the name implies, meaning that there's nothing acting on it except for gravity and, in some cases, air friction. Essentially, there's no engines on it, there's no one holding it or pulling on them, there's no parachute or anything like that. They just really have gravity acting on them. Technically, though, any projectile that's in the air is free fall. So we're usually going to refer to only the ones where it's dropped as a free fall, and then everything else will just be, vertical projectile. But even throwing it up can sometimes considered a free fall because it's freely falling in the air without any forces except for gravity. So I just want to point that out there. And like I said, in the ideal case, the only thing acting on it is gravity. Through experiments, it was found that the acceleration of gravity for all objects is 9.8 meters per second down, meters per second squared down. This is true for all objects regardless of mass. Many questions are going to throw mass in there as a little red herring to make it seem like it matters, but it doesn't. So all objects are going to fall at the same rate. The one thing to note is this is down, this is a vector, so that direction matters, and we're going to have to make sure that we note that in the later problems, as we do with vectors in a certain direction. One thing that I also want to point out is that the AP, even though they say that the acceleration of gravity is 9.8, you don't really need to use 9.8. A lot of the questions actually use 10 instead, and they actually in the directions will say, you can use 10 for the acceleration of gravity. So, with the exception of a few lab experiments where you actually want to compare it to the correct acceleration of gravity, you really don't need to worry about, whether you use 9.8 or 10. Most practices I'd recommend just use 10. Um, so yeah, in all the equations that we have acceleration, we're just going to put a g. This g, it stands for the acceleration of gravity. Now, one thing to note about these free fall ones, this main type in particular, where objects are dropped, is that you kind of want to keep track of the fact that there's hidden pieces of information, and this is going to be true in a decent amount of these projectile questions. That the words are going to hide information. Now, we sort of saw that in the previous questions, the previous problems that we've done, where they would say the phrase, it comes to rest or it starts from rest as a way of kind of hinting that the initial or final velocities are zero. Or they might say that it returns back to where it came from as a way of, hinting that both the position values were zero. It's going to be sort of the same idea where certain phrases in the sentence and the problem are going to hint at very specific values that you know. So if we read this question, a ball is dropped from a height of 5 meters. How long does it take for the ball to hit the ground and with what velocity? At first, it doesn't look like we have enough information. We have one value, 5 meters. How are we supposed to find time and velocity? We need at least two, maybe even three other variables depending on what we're looking for. So we can actually get a lot more information from here. Now, one thing that we know is that since it's falling freely in the air, we know that the acceleration is 9.8 meters per second squared. One thing to note though is I'm going to want to actually make sure that this is a negative 9.8 meters per second squared because it's going down. Just to make life easy, especially once we start dealing with the throwing the ball up, throwing the ball at an angle, and all these things, It will make everything significantly easier if we just constantly say that down is negative. Technically, you are free to set the direction convention however you want. If you want to say that down is positive, that's fine. Though it does get a little bit tricky keeping track of it. So, what I would recommend is wait until you are really good at setting up these problems where you can read this problem and immediately solve free falls before you start worrying about, altering the sign convention so that down ends up being positive rather than negative. Now, another piece of information that we know is that the ball was initially dropped, meaning that that initial velocity is also zero. We can also say that either the initial or the final positions are zero. Once again, it's really kind of a reference thing. We can either start the problem right where the ball starts and say that that location, that is position zero, and that anything going up is a positive position and anything going down is a negative position. Or the way I tend to set it up, I try to put the very lowest part of the motion as zero. So if you have an object being dropped, can't draw that. If you have an object being dropped from some height, like right here, and that's 5 meters in the air, what I would say is the ground is zero and the initial dropping location is five. Um, like I said, it really doesn't matter how you do it. You can even set, this middle point to be zero, and that would make this positive 2.5, and then that would make the ground negative 2.5. And you can actually play around with that and you would see it ends up being the same thing. But just to make life easy, set the lowest possible point as zero, unless they don't tell you how far it goes down, in which case you can just set the initial position zero. Yeah, so this kind of says the same thing that I said before, that direction's relative. You can choose whatever direction you want as positive or negative, but just for now, I would say stick with down as being negative. All right, so here's the first question. Pause the video, work itself. Go over in a second. All right, so we are going to go through all the different variables that we have. Now, we have a lot. We have initial position. Like I said, I'm going to consider the case where the ball is being dropped from some height, from the 5 meters up in the air. And then I'm going to consider the ground to be zero. So the final position when it actually does hit the ground is going to be zero. Since it was dropped, I know that the initial velocity was zero. I don't know what the final velocity is. Now, this is something that a lot of students end up making a mistake with. Eventually, the ball, in the real world, when you drop a ball and it hits the ground, we know that the ball comes to zero. It comes to rest as it stops because of the floor. However, in physics, when the ball interacts with the floor, that's considered a change in the problem. That changes what's going on. And that's a different type of problem than the object falling. So, whenever we talk about the object hitting the ground, we're actually talking about the second right before it actually hits the ground. Or if you would like, uh, you can imagine that there's an imaginary sensor on the ground that when it strikes, we can read what that velocity was that it hit it with. Basically, the idea is that we are not looking at the moment after it hits the ground. It's always the moment right before. So the velocity is not zero, it's some number that it's hitting the ground with. Again, we know that the acceleration is negative 10 meters per second squared. Again, I'm keeping that convention that down is negative, and I don't know what the time is. It really doesn't matter which one I use to solve this. For this first case, I'm going to start solving for time. So I have my positions, my initial velocities, acceleration, and time. So I can use the annoying x's equation, plug the numbers in. A lot of terms drop out because of the zeros, and I end up getting that the time is equal to 1 second. Now that I have this time, I can actually use any other equation to find the final speed. I could use the timeless equation or just because it's a lot easier, I'm going to use this one, the acceleration equation. So v equals v naught plus at, plug the numbers in, and you end up getting negative 10 meters per second. Now this is important because that negative 10 is telling me that the final velocity is down, which again makes sense. When you drop the ball, it starts moving down. Therefore, the final velocity should be a negative value. One thing to note is that if we did use the timeless equation, so I'm just going to write it up here. If we use the timeless, we will still get the same magnitude value. So this would end up being the square root of 0 plus 20 times 5. So that would be 100. So the square root of 100 is 10. However, as you know, technically 100, the square root of 100 isn't just positive 10, it could be negative 10. So this is a plus or minus 10. And what you would do when you do this is you have to think logically, should the velocity be positive or negative based on convention? So knowing that the object goes down, you would cross out the positive and it becomes a negative 10. A lot of people don't remember to do this. So typically I try to keep the timeless equation as a last resort. I try to use the annoying x's and the acceleration equation as my main ones. And if they don't work, or at least they're hard to deal with, then I'll pull out the timeless equation. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, here, instead of dropping the ball, we're now going to throw the ball. So a lot of the variables stay the same. So again, my positions are still going to be 5 initially, 0 at the end. Now though, I do have an initial speed. And again, I need to be careful with my sign. So this is being thrown towards the ground at 9 meters per second. So I'm going to make this a negative 9 meters per second. Then I do final velocity again, acceleration, and time. It's important that you make sure that you put the negative. Now, in these cases where the object's going straight down, realistically, you can drop the negatives. You might still get the same number if you have one of the numbers negative, one of them positive. It's not really a big issue. However, once we have the object being thrown upwards, and it's in that scenario where the velocity and acceleration are in different directions, that's where it becomes extremely important that you put signs where they belong, and you make sure that one of them has the negative. But again, if you get into the habit right off the bat of putting negatives for anything that's going down, it just makes your life easy and you will never have to worry about that. All right, so the issue here is I can do the same method as before. I could do the annoying x's to find the time, but now that I have this initial velocity, I'll end up with a quadratic equation, which will require me to use the quadratic formula. It'll end up being x equals 5 minus 9t minus 5t squared. And then you'd have to plug that into negative b plus or minus the square root of b squared minus 4ac all over 2a. But you don't have to do that. You actually can use the timeless equation. I know I made the comment, I try to avoid this, but I also try to avoid the quadratic equation even more. So it really comes down to what you're more comfortable with. So you take the timeless equation, you plug all the numbers in. I'm finding the final velocity before I find the time. And then once again, when I take the square root, I get plus or minus 13.5. Take the negative because it's going down. Now that I have the final velocity, I can use the acceleration equation, plug the numbers in, and use this number to this equation to find time to be 0.45 seconds. And again, we can compare it to the previous question. It makes sense. If I throw it down instead of dropping it, it should hit the ground faster. And it turns out it hits the ground almost half as quickly. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So very common thing with motion graphs, you should be able to know what the graphs look like for the three things. These graphs in particular are, I'm actually taking into account direction, so they are the vector versions. You might see the graphs looking more where everything's above the x-axis as more of like the magnitude values. It ends up being kind of the same idea, except the x graph kind of ends up looking a little bit weirder. But normally, whenever you're being tasked with drawing motion graphs, I always recommend doing acceleration first, because acceleration in this class is always constant. It's either constant zero, constant positive, or constant negative. So technically, there's only three choices. Um, that that's not the same for position, because position not only can be constant, it could be linear, linear up, linear down. It could be linear from the positive direction, linear from the negative direction, or it could be curved. And again, there's multiple curves, multiple orientations. So acceleration is always easier, and then I work backwards. So when objects fall, they accelerate at -10. So I end up having a negative constant acceleration. Because the acceleration is constant, I know that the velocity graph's slope must also be constant, because the slope of velocity is acceleration. So I'm looking for a linear graph here. Now, if I'm dropping the object in free fall, the velocity is going to start at zero and then go down. Once again, this makes sense because the slope of this is a negative constant value. This graph is a negative constant value. So far, I have two of my three graphs. Now I have to worry about the position. This one's a little bit tougher, but we're kind of going to do the same thing. Whatever this graph does is telling me what the slope of this does. Since I'm dropping this object and it says that zero position is the surface, that means that this is where it initially is, and eventually it's going to land on the ground. So it starts at some initial position, it's going to fall until it reaches the final position on the surface. Now, according to this graph, the velocity starts zero and increases in the negative direction. So it goes more negative. This graph should have a slope that starts zero and becomes more negative. So my position graph will end up looking like this. It looks like a very defined parabola. That's going to be actually really common for a lot of these projectiles in the vertical direction, is that they're going to look like projectiles regardless of how it is. If it was dropped, if it was thrown down, thrown up, or thrown at an angle, all that changes is that the parabola may be shifted over a bit. So you might see this parabola shifted over so that it looks more like this, where it goes up and then comes down, instead of just being going down. Or maybe it might be shifted so that it starts partway through in its motion before going down. In all these cases, though, it ends up being the same type of parabola. So as long as you get the idea that's a parabolic function, you end up pretty much getting a good idea of what it could look like. So we're going to leave our discussion about free falls and some of the early vertical projectiles there. Later on, we'll talk about how to actually deal with throwing objects up and how to deal with cases like air friction. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.